Okay, good morning everyone. Welcome to the 23rd lecture. Yeah. Okay, so by the way, if you didn't see, so there is a lecture-wise file in the Google shared folder. Please have a look at it in case if you wanted a lecture-wise details. Okay, so yeah, summaries of each lecture is given there, and also partially the future plan is given. Yeah, so please have a look at it if you haven't already. Okay, so towards the end of yesterday's lecture, we were looking at Metroid's minimum weight maximum independent set or basis problem. That is, given a Metroid, perhaps implicitly, with the weight function, weight attached to each element of the ground set, want to compute a basis such a way that it has minimum weight. So the dual version is a maximum weight problem. That is, you want to compute a basis of maximum weight. In fact, even that admits a similar algorithm. We'll not discuss it. It's basically a dual of the minimum weight version. So the simple greedy algorithm was the following. We just modified Metroid greedy, where we would greedily pick an element from the ground set and construct the independent set, and guaranteed that we'll end up in a maximal independent set or basis because of Metroid's property, exchange property. Okay. So now all we did was we sorted edges in ascending order of their weight and then chose. So only thing that we did is our choice was guided by their weights. Okay. So every time we'll be picking minimum weight candidate. Okay. We proved the correctness. So essentially an inductive proof. The crux of the argument was if you assume our greedy had comparable or better weight until I minus 1 iteration. So if you just look at the ith iteration, so the ith iteration, so we argued that the candidate we took at the ith iteration, that is ith element picked by greedy, is bounded by some element in the optimal, which has weight smaller than or equal to ai. Okay, so that means element by element. So G1 has weight at most that of A1, G2 has weight that at most that of A2, and so on. GK has weight at most that of AK. So by induction. Okay, so if you see this as an inductive proof. So like one of you pointed out in yesterday's lecture, so the optimal, if at all, it should match the greedy. So the weights should match the greedy, right? It cannot be smaller. It has to be at least larger, but this is claimed to be optimal. So then only possibility is it matches the weight. So this will be equal to that of greedy. This will be equal to that of greedy, and so on. They may not be the same choice because there could be multiple elements of the same weight. So the solution may not be the same, but at each iteration, the weight will be matched by greedy with that particular element of optimal. Okay. Yeah. Any question on this? So if there are no questions, we'll see an immediate application of this to the minimum weight spanning tree problem. Okay. So this is fairly popular problem taught in most of the algorithm courses, first course on algorithm. So we are given an undirected graph where edges are given weight. So each edge has a weight. For simplicity, we'll assume it is non-negative. It really does not matter. Even negative weights, it will work. Okay. The output is a minimum spanning tree. That is minimum weight spanning tree. A spanning tree whose total edge weight is minimum. Okay. Now, let's consider the graphic matroid of G. So we know that the base, so we have a connected graph. So the bases of the matroid are nothing but spanning trees of G. Okay. So The MST problem is nothing but computing a minimum weight basis for the matroid, graphic matroid M, which is given implicitly as G. So we are not given the matroid, we are only given the graph. Okay. So we know implicitly what is the matroid. This is called implicit representation of an object. So in this case, the object is matroid. Okay. So like I mentioned in this problem description, so the matroid is usually not given in explicit form. Say, what is explicit form of a matroid? Just simply listing the independent sets. Okay. So only problem with this listing is, in general, people don't consider such representation based because the size of independent sets could be exponential in the number of elements in the ground set. Say if the number of elements in the ground set is n, then number of independent sets could be potentially 2 to n or something close to it. Okay. So many a times people like implicit representations of matroids. For example, graphic matroid is an implicit representation. So unfortunately, not every matroid is a graphic matroid, but it's certainly a special class of matroids. Okay, so that's why I've written example as a graph. So there are also other forms of matroids. There are also other forms of implicit representations of matroids. We will not really look into it. So for example, linear matroids, there is also something called transversal matroids and so on. So yeah, so that is something that we need to keep in mind whenever we talk about this matroid independent set problem. The matroid most likely given to be in implicit form. Okay, so here, so now the MSC problem can be viewed in that angle. So here we are given the matroid in an implicit form. All we need is a minimum weight base. Okay, or minimum weight basis for the matroid. So the algorithm is pretty much the same. I've just changed slightly. So you just order the edges in ascending order. Now all you check is, so I union EI is independent or not. How do you check? The resulting graph should not contain a cycle. Okay. So if it contains a cycle, you cannot include that edge. Else you can, because independent sets are acyclic subgraphs, right? Okay. So this algorithm is nothing but the very well-known Kruskal's algorithm. Okay. So this is known as Kruskal's algorithm. So what we have done is, with this matroid view, at one shot we have correctness of Kruskal's algorithm. Okay. Yeah. So whatever we have observed so far immediately gives us correctness of Kruskal's algorithm. In other words, Kruskal's algorithm is a special case of our matroid greedy algorithm. Okay. In fact, weighted matroid greedy algorithm. Yeah. So just to demonstrate, so let's take this example. Let's quickly run Kruskal's algorithm on it. So minimum 8 edge. Let's take this. So maybe use it slightly thicker. Okay. So minimum weight edge. So there are still edges of weight 1. I'll take this as long as it does not form a cycle. There's no further edge of weight 1. So then I'll take edges of weight 2 as long as they don't form a cycle. Are there more edges of weight 2? Weight 2. Then we'll take edges of weight 3. This is it. Oh, sorry. This is it. This is it. And here it does not make a cycle. Did we exhaust all of them? No. So now this edge of weight 3. Any more edge of weight 3 left? No. And then we go for edge of weight 4. This one creates a cycle, so we cannot take this. This one also creates a cycle. We cannot take this, but we can take this. Then edge of weight 4, this creates a cycle. Anything else? So then we'll pick edge of 85. Okay, so this is one minimum spanning tree. Okay. Yeah. Yeah. Any questions? So I believe people have seen Kruskal's algorithm already, right? Yeah.
So just one
So
question.
yes. Yeah.
Can you give some practical examples where this can be used to find, like, if you find a minimum spanning tree of a graph, what are the applications
Mhm.
of that?
Oh, I'm not a good person for that. I mean, there are of course applications, but I am not an applied person, so I'm not going to give applications. Okay.
Okay, sir.
Yeah. So if you go into networks, you'll see wide applications of minimum weight spanning tree. Because if you want a minimum connected graph, right? Minimum weight spanning tree is something. Yeah.
Okay.
Okay. In the remainder of the lecture, so our objective is, so we'll briefly see the scheduling problem with the Metroid view, and then our focus will be back on Kruskal's algorithm. Okay, so the main problem here is we didn't do a complexity analysis of this algorithm yet. Okay, so we are going to do a complexity analysis. So we'll see that this is an interesting part. Okay, so that is where enter the data structure problem. So we'll see how to implement this fairly efficiently using what we call as disjoint union data or disjoint set data structures. Okay, so that is going to be our main theme for the next couple of lectures, maybe 5-6 lectures, where we'll see implementation issues in the sense that even when you have an algorithm, so how do you do this efficiently? It becomes a main challenge. For that, we'll need fairly efficient data structures. Okay. Okay. So let's just quickly look at the scheduling classes problem. Okay. So where we are given a set of n tasks with the given start and finish times. Okay. So what we want is a maximum conflict-free schedule. That is a schedule such that their intervals, that is their periods or intervals of the class time intervals don't overlap. Okay. So let's take this example. So let's demonstrate everything through this example. So we saw that greedy algorithm works, right? So if you sort the task by earliest finish time or sort the task by finish time in ascending order, and you pick greedily add tasks, so we saw that we'll get an optimal solution. Okay. Now, how do we explain it through Metroid perspective? So we saw that matroids kind of represent the greedy property, right? Or the greedy choice property, as well as optimal substructure property. So what we know is if the solution space admits matroid structure, then certainly greed algorithm works. But if you look at this, uh, so what is a candidate for independent set? It has to be feasible solutions, right? So if you take set of all feasible solutions, that is conflict-free schedules. So let's see if it has a matroid structure. Like I had mentioned a couple of lectures ago, it does not have a matroid structure. Because if you take, so task 2, 4, then you can schedule 4, 8. Okay, so these two tasks. This becomes maximal. Similarly, if you take 1, 4, then you can include only 4, 8. So this also becomes maximum. Whereas there are schedules with more than 2 tasks. So if I take 1, 3, 4, and 4, 8, this is one task, better, larger than this. So similarly, this is even larger. This is perhaps optimal. Okay. So if you take maximal schedules themselves, so they are of different cardinality. So hence, there is no matroid property there, right? So if you take this as all feasible solutions as an independent set, that is set of all conflict-free schedules as independent sets, then yeah, I mean assuming that empty set is also a conflict-free schedule. then even then this does not form a matroid. So then how do we explain the greedy algorithm here? Well, I mean, we have proven correctness, so that is not an issue. But still, in this case, there is also a matroid structure, which is slightly subtle though. Okay. So what we do is, if you take set of all maximum schedules, okay. So let me call this as collection capital B. Okay. So in this case, maximum schedule is 1. Is there any other maximum schedule you can think of here? I think this is only one maximum schedule. So for this example, there is only one maximum schedule. Is there anything else? Not maximal, maximum schedule. That is largest cardinality. Okay, so in this example, there is only
Sir, what
yeah.
is the difference between maximal and maximum?
Maximal is something that you cannot add any further. Maximum is of maximum cardinality. That is the largest possible cardinality. So for example, this is a maximal schedule. You cannot add anything further. Okay, this is a maximal schedule. Whereas this is maximum because among the maximal schedules, this is of largest cardinality. Okay. So maximal means it's maximal with respect to containment. You cannot add anything further. So for in any example, right, and any of the problems, maximal solution is something where you cannot improve it any further. Maximum is best among all maximal. Yeah. Did I make sense?
Yes, sir. Yes.
Okay. Okay.
Sir, one more doubt.
Yes.
So,
Yes.
if the problem is some optimal solution finding problem, and if the solution space admits a Metroid, then we can go for a greedy choice always, like greedy algorithm
Yes.
always.
Yes. Yes.
Okay.
Always. Yeah. Yeah. So that is the takeaway. So this matroid greedy algorithm is a generic algorithm that we have presented. So any problem which admits a matroid structure. So as long as checking for independent set is cheap. Okay. So this algorithm, what we need is this should be cheap. It should not be costly. Okay. So this should be efficiently implementable. Then, so we have efficient greedy algorithm for that problem. When I say efficiently, so say if this runs in n square time, then overall in n cube time you can implement this algorithm. Okay, that way.
So,
Yes.
say the problem solved using the Metroid and the problem solved using the problem solved using Metroid is strictly a subset of the problem solved using greedy.
Yeah, that's kind of. I mean, so for example, the storage of files, right? So you don't have a matroid structure there. So if you look at our very first example for greedy, right? There, see, the problem itself is such a way that you are not basically, the solution is not a subset, it's an ordering. So in that case, it's not easy to define a matroid. Okay. So if you put restriction, so if you say my problem is to come up with a subset, okay, optimal subset, whatever, then yes, then any algorithm, any problem which admits greedy, there will be a corresponding matroid. Because this greedy choice is essentially saying matroid exchange property. But otherwise, there could be other problems where you are not computing a subset. There could be some ordering problem or any other kinds of problem. In which case, you cannot have matroid. So hence, so greedy algorithms with the matroid structure is a strict subset of set of all problems with the greedy algorithms. So that way, yes.
So suppose there is a problem in greedy that doesn't admit Metroid structure,
Yeah.
then how could we know whether it will? By seeing the problem, could we know that whether it will give the correct output in the greedy algorithm or not?
See, for the greedy algorithm, I mean, as far as I know, I mean, the best way to check is to see if the exchange property holds. Okay, so you have an optimal solution and you look at the greedy solution. Now, if you replace the optimal values or values in the optimal solution by the greedy values, if the solution size, you can ensure that the solution value or solution size does not increase or does not go bad, then you know that the greedy algorithm works. But as far as I can see, any such algorithm, if you are going to construct a subset, it has to be Metroid, because it's essentially the exchange axiom which comes into play. See this, even the exchange argument, right? So when you swap your greedy choice with the optimal value, right? That's basically a Metroid exchange axiom, right? Coming into play, the axiom I3. So that way, for any subset construction, that is a problem which actually wants you to output a subset which is of optimal value. If it admits greedy, then there has to be a Metroid. I mean, Metroid will be, in fact, all feasible solutions. In some cases, it may not be all feasible solutions. You may have to restrict a bit. We'll see in this case of scheduling. Yeah. Did I answer your question?
Yes, sir.
Sir, there
Okay.
can be only
Yes.
one type of like only one greedy solution, or there can be multiple.
What do you mean by one greedy solution?
I
You mean
mean, because
one specific algorithm, you mean?
no, one specific solution set. Like you were saying now that you will compare with optimal, and if you can replace with another one element such that both of them are equal in size, you're saying in something in that line, no, sir?
Yeah. So that does not mean that there is only one greedy solution. Okay. So even greedy, you might have choices, right?
Okay.
Okay. So at some point, so for example, even the spanning tree implementation, right? There will be multiple edges of the same weight.
Yes, yes.
Then which one will you choose first? So that
Yes.
each of them might lead to a different solution.
Yes, yes.
It is possible.
Yes,
So that way, solution may not be unique, but all the exchange argument would say that greedy, you can always take optimal solution and compare it with the greedy solution. So you can replace the elements from the optimal solution with the greedy wherever they disagree, so that your solution value is still better. Okay, it's minimum, smaller if you're looking for minimum, larger if you're looking for maximum. So yeah.
Okay, sir. Okay, thank you.
So the trick here is simple. So what you do is you just take set of all maximum schedules as set to B. Okay, that is going to be our basis for the Metroid. Now you look at all subsets of B as independent set. So these are feasible solutions, but only such a way that there is an optimal solution sitting above it. So basically, we are throwing away these. So we are not considering any of these schedules. So we are considering only, say, for example, in this case, we are considering this and taking all subsets of it, including the empty set. Okay. So if you consider that, then this happens to be a Metroid. I'll leave it as an exercise for you to prove. It's a fairly simple argument. I mean, in fact, our exchange argument, the correctness proof itself immediately gives it. Okay. So yeah, so here there is slight change. So see, here there is a slight subtlety. Okay. So we could not take the set of all feasible solutions as a candidate for independent sets of the Metroid that we are looking for. Okay. So that will not work. It's more about the peculiarity of this problem. Okay. So because you can really have classes which stretch the whole day or the whole afternoon, then you cannot take anything in between. Okay. So that will kill. So even if it is maximal, you cannot grow it into an optimal. So the moment you throw out all of them, you only consider the ones which lead to maximum. It gives us a Metroid structure. Okay, it's kind of an artificially built Metroid structure. It's not very natural, but still there is a Metroid structure. It's because when you, I mean, the reason is in our greedy algorithm, right? If you are looking at earliest finishing task, we are essentially ensuring that we are going to hit one of these guys with the maximum schedule. So that's what happens. Okay, so that's a kind of reasoning, though it's not a complete justification. So in that way, for any greedy algorithm which constructs a set and is optimal, there is always a Metroid. But the only thing is, I mean, it could be that your algorithm itself cleverly, so our greedy algorithm here cleverly avoids this. That's what happens. So when you sort the tasks with respect to earliest finishing time or finishing time first, then earliest finishing time first, then you actually avoid this. That's what happens. You'll never pick elements so that you will end up with this. That's what happens. Okay. Okay. I have a short reading exercise. So yeah, since we spoke about scheduling, so there is also a nice scheduling problem with the deadline where the tasks are of unit time, but there is a deadline, and if you miss the deadline, then there is a penalty. Okay. The CLRS book in section, I think 16.5, gives a clear, complete detailed argument about the Metroid structure and so on. It defines a Metroid and proves that it's a Metroid, and hence there is a greedy algorithm. Okay. So we have already spent a lot of time on greedy. So we will not be looking at it in detail because it does not add something new completely. I mean, it's similar ideas, but I request you to go through it. Okay. Yeah. So it's there in the third edition. I don't know, earlier editions have it. I believe they have, because new editions are only more problems or exercises, is what I believe. Maybe a couple of sections, I mean, a couple of chapters are new, but yeah. Okay. Yeah, I'll pause for a minute if there are any questions so far.
Hello.
Yes, yes.
Sir, the scheduling problem, have we
Yeah.
gained anything by comparing it to the Matroid structure? Because we just changed the entire independent set space. Initially, we thought it is all the possible solutions. Then,
Yeah, no, here the only message I wanted to say is, like, whenever there is a greedy algorithm, particularly a problem which basically constructs a subset, there is always a Matroid. Okay. But yeah, so you're right. I mean, we didn't really gain anything. It's just that I could show you a Matroid, that's all. So in this case, and if you had started off with this as a Matroid, you would not have got a greedy algorithm at all. No. So taking the Matroid view right away may not give you greedy solution always, but in many cases it does. So in this case, it was a peculiarity of the problem itself. The problem itself was fairly peculiar because there could be elements which can conflict with almost everything, and hence they could be maximal. So once you eliminate that, what you get is greedy. I mean, Matroid structure, sorry.
sir, okay, so for this scheduling problem, Matroid structure has been found. And you were saying there
Yeah, so
was,
I mean, I just demonstrated that you can form a Matroid, but yeah, like you said, it's not the Matroid structure which gives you immediately the greedy. Okay, so the greedy actually, it's you didn't get it from the Matroid structure, right? Matroid structure we got from the greedy algorithm. Okay, here it's not Matroid structure which led to the greedy. Okay, so greedy was because of the exchange argument. Even if the exchange argument was valid, there was no Matroid structure in the solution space. Okay, so the only thing that I did is I just demonstrated. So you can construct a Matroid. What we are doing is, so see, what is this Matroid? So this is the solution space where your algorithm is actually outputting. So these are a set of all possible solutions your algorithm can potentially output. Okay, so the algorithm doesn't even go to these maximal elements. It will never output these. So if you look at the solution space, which is the algorithm could potentially output, there is a Matroid structure. But in the problem, there is no Matroid structure. Okay, that's what. Or in other words, you can say that the greedy algorithm somehow created a Matroid by looking at only the optimal solutions. There it had a Matroid. Yeah.
hello?
Yes. Yeah.
Sir, you said the greedy algorithm is creating a Matroid. We
Yes.
are creating a Matroid with the solutions of the greedy algorithm. It is not creating. It is just giving us the optimal schedules.
No. So what I mean is, so greedy basically eliminates all those sets which violate the Matroid property. So that's what it does, right? See, implicitly, that's what the algorithm does. Greedy algorithm basically searches a space which looks like a Matroid. Okay, so
Yes,
this
yes.
is essentially the search space of greedy algorithm. Greedy algorithm never explores any other set. So this capital B and its subsets, right? So this is exactly the solution space for greedy algorithm. So that is what. So implicitly, it is basically restricting itself to a Matroid, and we have defined it. That's all. So we took some effort to define it. That's all.
Does this happen with every case? Like we may not be able to see a Metroid, but the greedy algorithm itself.
No, you can. In principle, for a generic optimization problem, right? Like I said, it should not be about ordering or whatever. So it should be a subset. So the solution should be representing a subset. You can always prove it. If there is a greedy algorithm, that has to be Metroid, because this greedy choice property, right? That is basically exchange property. That ensures that all maximal solutions have the same cardinality. So it's, in a way, it's kind of equivalent.
Okay, sir.
But however, there could be greedy algorithms for problems which is not about constructing the subset. Prime example being our storage problem, where it's about ordering. Then you cannot have a Metroid. Okay, so then there is no Metroid structure.
Okay, sir.
Any other question? Okay. So now we are going to a slightly different terrain. We'll still be looking at greedy algorithms. So our next 4 to 5 lectures are going to, or maybe even 6 lectures, we'll be looking at data structures. Okay. So our data structures will be kind of centered around minimum spanning tree algorithms for minimum spanning tree. One is what we saw already, Kruskal's algorithm. There's also another greedy algorithm, Prim's algorithm. Okay, so there it does not fit into our generic Matroid greedy algorithm, though minimum spanning trees, spanning trees form a Matroid structure. The algorithm is slightly different. In both cases, the interesting part is, so to get optimal or efficient implementation or algorithms which are fast. See here, this is a meta algorithm, right? So the complexity depends on how do you implement it. Okay, we get interesting data structures. Okay, so our next few lectures are going to be about that, building those data structures and analyzing them. Okay, so maybe I'll just, so let's try to analyze the complexity here. Okay, so let's say number is, so number of vertices is, let's say, n, number of edges is m. Let's say. Okay, so let's analyze the complexity here. So what is the time required to sort the edges? So using any comparison based sorting, this order of m log m. Yeah, please go ahead. Okay, you wanted to say the same thing? So yeah, it should be m here. Okay, so I wrote it n because for Matroids we use that, but let's stick to m because later on we'll always be using n for number of vertices. Okay. Now this will run for m iterations. So this will be something into m into something. So how will you do this? So this is only task now, right? If the current set of edges along with the new edge, does it create a cycle or not?
Sir, if start point equal to end point.
Yeah, but how do you check that? So if you're given a graph, it contains a cycle or not? What is the algorithm for that?
Depth first search.
Yeah, either depth first or breadth first, right? Either of them will report a cycle. Probably BFS is probably faster in that regard. So, I mean, they might have essentially same complexity. So let's say BFS. So what is the time required for BFS?
V plus E.
Yeah. So let's assume that E is large. So it's like order of the size of I, right? This can be as big as order of M, or in fact order of N. That's it. Because essentially you're going to have a spanning tree which will have n-1 edges, right? So this is, let's say n, but order will come outside. This is order of mn. Okay. So in case where the number of edges is huge, say close to n choose 2 edges, this can be potentially big, right? Order of n cube. So if m is theta n square, then time is order of n cube. If number of edges is theta of n, then this is order of n square. Okay. Yeah. So, well, it's fine. It's polynomial time. That way it is fine. But it's desirable to have better algorithms, faster algorithms. Ideally, order n time or order m time. But something close to that is also good enough. So, can we reduce the complexity? Is our prime concern here now. Okay. So, yeah. So this is what we did. Okay. So with the naive implementation will be BFS or a DFS. You want to compute the cycle. So BFS or DFS would take linear time, right? Linear in the number of vertices and edges. So here we know that the number of edges in I is at most n-1, where n is the number of edges, vertices, sorry. Okay, so overall time for a naive implementation is order of mn time. So now let's see how to improve. So what is it we want? So if we reduce the time complexity of this step 4, say something like, say if you reduce it to root n, then my complexity will be order of m times root n. If I reduce it to order of 1, then this will be order of m. That is number of edges, right? It all depends on the complexity requirement here. Okay. So let's quickly look at this example. I'll just rework the example. I mean, we'll just rebuild the tree again, okay, very quickly. So let's just to try to understand, okay. So okay. So you're choosing this edge, okay. So at this point of time, my I will contain what? Edge 1. So whatever the endpoints are, okay. So yeah, I didn't write the endpoints here. So this particular edge it has to store, okay. At the second iteration, I'm adding this. So what is it I need to check? I need to check if this is a cycle, right? Now imagine a structure which actually maintains these trees. Okay, so I have this tree now. Let's call it as T1. This is T2. When I add a third edge, is there anything of weight 1 here? No, right? So now we have to look for weight 2. So when I add an edge, so what are the checks that I would do? If the edges between two elements in the same tree, then it's going to be a cycle, right? And in fact, it is if and only if. If the edge has one vertex in common with one of the trees, then it won't form a cycle. Or if it has no vertex in common with any of the trees, it won't form a cycle. So what are the requirements for us if you are going to maintain trees? So the imagination is I'm going to maintain these trees. Now, right now, they are only edges. Maybe if I add one more, it will grow slightly further. Yeah, if I add this, now this is no more an edge. Okay. So now if you look at these trees, so let's call this as T1, T2, T3. Okay. So imagine a structure which maintains these trees. Then what are the operations that I need to support? So one operation is when you add a new edge, the tree structure, whatever structure we are going to build, it should say, okay, the endpoints of these edges are within a tree or not, right? That's a prime thing. So if the endpoints are within a tree, then I know that that edge creates a cycle, right? So for example, if I take so this is also 2, okay. So now if at some point of time, if I get this as the edge, okay, so this is part of T1. So both endpoints are within T1. So that means we know that it's a cycle, right? So yeah, so if my edge was like this, so then we know that it forms a cycle. So if we are going to implement it this way, that is, the idea is you maintain trees, okay, you maintain trees somehow, so we don't know how, so that is our main job, okay. In that case, what are the operations that we need to support? When you have an edge, so when you pick an edge as a next choice for greedy, I want to know if the endpoints of the edge are in the same tree or not. Okay, if they are in the same tree, I'll throw away the edge because I know that it's a cycle. I don't have to run BFS now, right? This information is enough to know that the endpoints of the given edge are within the same tree, say T1 or T2 or T3 or T4, whatever number of trees that we have. Okay, and we should be able to support an arbitrary number of trees. When I say arbitrary, it could be as big as number of vertices or by 10, n by 10 or whatever. So omega n many trees. Okay. So what are the other properties that we need? We should be able to create a new tree easily. So when I add a new edge, so in the next iteration, so is there any edge of weight 2? So all of these are connected, right? Okay, so edge of weight 2, this one.
Next to 1.
Next to 1, that this
Yes,
one,
that
right?
one. Yes.
That we already added, right? So I'm just looking for something which we haven't added. So this one, oh sorry, this one. Anything else? Everything else is blue, right? Yeah, everything else is blue. Okay. So now if I add, so
One more, sir.
where?
T1.
This
The
one. Yeah,
inverted V shape.
got it. Yeah, this one, right? Yeah. Anything else? Okay, so this one I didn't even give weight. So let's put say weight of 4. Okay. So now what are the other things that so one first information is if when you get an edge, I want to know if both endpoints are in the same tree. So in other words, what I want to say, I want to know if I get a vertex, what is the tree it is contained in, right? So that is a second, I mean, it's a second task. I mean, it's if you know that task, you know how to check for an edge, right? You just look for each of the endpoints. What I mean is, given a vertex index, I want to know which tree contains that vertex. There may not be a tree which containing that vertex at all, or there could be a tree. In that case, you get the tree, and similarly for the other endpoint too, you run the same algorithm. Then you know that if both of them are in the same tree or not. In that case, you know cycle. But in case when the endpoints are not in the same tree, what are the possibilities? So one possibility is one of the endpoints is in a tree. So that is this case. In that case, you need to update the tree, right? Add a new edge to the tree. And in another possibility will be, okay, so how do I demonstrate it here in this example? Okay, in this example, I cannot, but I'll just do a fake demonstration, okay?
Sir, hello.
Yes.
Sir, when you are saying both the endpoints are not in one of the trees,
Yeah, in the same tree. Yeah.
aren't we checking for a cycle?
No, no. When that's what, right? So when we say that both endpoints are in the tree, that means we have a cycle. If it is not, it's not a cycle,
So
right?
how
So
are we
that
checking that?
sorry.
So how are we checking that?
No, so for that you just need this information, right? So say xy is my edge, okay? So I want to get a tree index which contains x, a tree index which contains y. You need to just see if these are the same trees or not. Okay. Now, assuming that, I mean, I'm not worried about the complexity here. So if it supports this operation, so then all you need to do is see if both of them are in the same tree. If it is they are in the same tree, we know that there's a cycle. Otherwise, it does not form a cycle. That means that edge has to be added.
So are you checking the like vertex set of each tree? Like you take
No, no,
T1,
no,
take,
no. That is the job of the data structure. So right now, I'm not worried about the complexity at all. I'm just coming up with the idea.
okay, okay.
Okay, so that is the job of the data structure. Okay, so how does it really check this? Usually what it does is it will be having a representative set for each tree. It will spit out that representative vertex. Okay, so you see if the representative vertex for x and y both are the same, that means they are in the same tree. Okay, so it won't be like you are checking these sets right away. Okay, so now what if they are not in the same tree? That means this edge has to be included, right? So there are two possibilities for this edge. One is this edge it has one of the vertices in one of the trees, or both vertices are in two different trees. So say 4 in this case. Okay, so that means you have to merge the two trees. So here you'll have to merge the two trees. There could have been a possibility that you extend, that is how do I, yeah, so in this case, so if this edge, one of the endpoints is in a tree, the other endpoint is not, so in this case you need to extend the tree by adding an edge. Okay, there could have been a possibility where I was adding this before adding this edge. So I was adding this edge before adding this edge. In that case, I would be creating a new tree. So the third operation that we want is creation of new tree. Okay, so if we are going to have this kind of implementation where we are maintaining trees, so we need to understand how to implement each of these operations. That is, one is for cycle checking, which is basically given two vertices, see if both of the vertices are in the same tree or not. Second, how to update. So it's basically dynamic data structure. So data structure keeps on changing. You're keeping on adding trees, or maybe even merging trees. So in this case, you have to merge two trees with adding an edge. Okay, in this case you will have to extend a tree, and yeah, in some cases if you are adding an isolated edge, that means you are creating a new tree. Okay, so these are the operations this has to be the data structure has to support. Okay, so this is a more formal description. Okay, so the data structuring problem is we need to maintain trees, a dynamic set of trees, where we are allowed to create a new tree with a given edge. So given an edge such that u and v belong to two different trees, merge them into a single tree by adding, or given a vertex, find which tree it belongs to. So I'm assuming that this find operation, which actually gives an index of the tree, so that to check if an edge endpoints of both endpoints of an edge belongs to the same tree, you just need to compare that. Okay, so this is what we call as disjoint tree data structure. Yeah. So to implement this, so there is a better way. So all we do is we view them as sets. Okay, so this is called disjoint set data structure. Okay, this is a more general problem. So we will see easily that this actually, so if you support this, then our problem is solved. That is disjoint tree data structure problem is solved. So here we want to design a data structure which maintains a collection of disjoint sets, which is dynamic. Okay, so this is dynamic. That is, number of sets can change as well as sets can change, which supports the following three operations. One is, given an element X, it should create a new set with X as the only member. The second one is the union operation. So given two elements, we want to merge, that is take the union of the sets that contain X and contain Y. Say Sx be the unique set containing X. So one thing that we want is these should be disjoint sets. Okay, so hence if at all there is a set containing X, it will be unique. If at all there is a set containing Y, it will be unique. We need to obtain union of this. The third one is the find, that is, given X, find the set which contain. So when I say find set, how do you want to output it? Okay, so here the understanding is each set has a representative. That is something I haven't written it here. So each set has a representative. So it can be that way, representative element. So then in this case, output the representative element. Because if it outputs a set, it's going to be difficult to manage sets. You have to compare sets and so on. Representative element. Okay. Yeah, so this is the task that we are going to look into in the next lecture. Okay, so next couple of lectures, we are going to show that there is an efficient implementation so that overall time, it may not be per iteration, the overall time required to implement whole of this will be something like order of m plus n. Okay, so unfortunately we cannot have a data structure which per operation does in time order 1, but what we call as amortized, that is, if you add up everything and then look at the overall running time, it will be order of m plus n. So that is going to be our primary task for the next two lectures. So the next lecture we'll see a simple implementation of disjoint set data structure, and then we'll see a more involved implementation as well as analysis, which gives fairly fast support for these operations. Okay. Okay, so I'll stop here now.